Good morning, everybody, and thank you for joining us today. My name is Duncan Rowe. I'll be hosting the event this morning. Before we get into Hemi's presentation, just a couple of housekeeping points. So the seminar today, webinar will be about 40 minutes long. Depending on how many questions that we get, we'll save some time at the end for those as well. The event is being recorded. But if you do want to ask any questions of Hemi throughout, just pop them into the Q&A box. We'll get to as many as we can at the end. Any that we don't manage to get to, we'll obviously contact after the show. And the recording will be available for all of those that attended if they do want to share with any colleagues or to re-watch. So without further ado, I'm going to pass you over to my esteemed colleague, Hemi Baldock, who's going to be presenting today. Over to you, Hemi.
Thanks, Duncan. Thank you all for joining today. Today we are going to be covering the Agilent 990 Micro GC. This is a system which can provide vital answers to your gas samples in a compact footprint, whether you're looking at locating natural gas deposits, evaluating biogases, or monitoring well efficiencies, or even measuring samples in the lab. The Micro GC offers you fast and reliable results. The Agilent Micro GC combines innovative and industry-leading features with the quality and speed that are critical to your gas analysis needs. So today's agenda, what we're going to do is we're going to do a really top-level overview of gas chromatography as a technique, and then that will lead us nicely into what is a Micro GC. Then we're going to talk about channels, which are really at the heart of the Micro GC. Then we'll go through principle of operation of the system, and then some associated accessories and software, and then we'll finish on some real-world applications. So just starting right at the beginning, what is gas chromatography? Gas chromatography is an analytical technique for the separation and analysis of a sample in gaseous form by separating out individual compounds that make up a sample mixture. So on the screen, you can see a schematic of a gas chromatograph, and we'll just walk through that process quite simply. So there are several ways to introduce your sample into a GC. Typically, you inject your sample in gaseous or liquid form in the flow of an inert gas, which we call a carrier gas. And this is often referred to as the mobile phase. This combination of sample and carrier gas travels through the flow path of your system in the constant flow of inert gas and through a column located in a temperature-controlled oven. The column is then referred to as the stationary phase. There are plenty of options for columns, and they can come in a variety of polymeric materials, as well as coming in different lengths, inner diameters, and film thicknesses. A specific column is chosen to be optimized for your separation of a specific application area. So the rate at which an analyte passes through the column is affected by the interaction with the material inside these columns. And this could be due to size and weight of your analyte or its chemical properties. The time in which it takes an analyte to pass through the column and reach a detector is referred to as retention time. So as you can see on the right-hand side, we have a chromatogram there, and this is how our data is presented. So you have detector response on the y-axis against retention time on the x-axis. Gas chromatography as a technique has many analytical applications, from routine monitoring all the way to unique research application areas. The technique is used across many sectors, including areas such as environmental monitoring, chemical and energy industries, and the food, beverage, and forensics application areas too. This is just to name a few of the many application areas there are. So what I've done here is I've covered a general overview of gas chromatography as a technique, and what we refer to as benchtops. The Agilent Micro GC is based on the same principle of separation and detection as the benchtop GC, but shrunken down onto a much smaller scale. This is a dedicated gas analyzer. While I'll make comparisons to benchtop GCs, it's not a direct replacement for benchtop. Both have their specific strengths, and we'll explore the micro GCs in more detail today. So there are three main aspects I'm going to cover of the micro GC today. Its size, speed, and flexibility. Here on the right, you can see a picture of the micro GC system, which is roughly the size of a shoebox and weighs only 7 to 8 kilograms and is a really compact, portable system. As well as having this small physical footprint, it also has a small environmental footprint in the lab as well, using roughly around 10% volume of carrier gas and 50% power usage of that of a typical GC. Another really nice feature of the micro GC is its speed. So it offers really rapid analysis times, with run times typically averaging around 1 to 2 minutes. The system itself works isothermally, opposed to benchtop GCs, which ramp. So this gives you really quick startup times and no delays between each runs. Compared to benchtop GCs, this system is specifically for targeted gas analysis, with the exception of liquefied petroleum gas and liquefied natural gas. And the micro GC is a really flexible system. This can be used as a lab analyzer, but also due to its size and portability, can be used out in the field and for process monitoring as well, and also has specifically designed self-contained carrier case with built-in power and carrier gas features for truly portable gas analysis. So at the core of the micro GC is what we refer to as channels. Each channel is a complete miniaturized GC, which has dynamic electronic gas control, micro machined injector, narrow bore analytical columns, and a thermal conductivity detector. And each micro GC can house from 1 to 4 independently controlled micro machined GCs, or channels, as we'll refer to them throughout the webinar. So just to go into each of those parts and their function within the micro GC, the electronic gas control controls the flow and pressure of carrier gas. And the micro GC is compatible with helium, argon, nitrogen, and hydrogen as a carrier gas. This also controls the backflush capabilities of the system. Backflush offers protection for the column against interference, such as heavy compounds, but can also be used to shorten runs by venting those later eluting compounds as well. We then have the micro machine injector, or MEMS injector. This controls the injection into the 10 microliter sample loop. This can be held at temperatures up to 110 degrees and is set depending on your requirements of your specific application. With the micro GC, we're working with really small sample volumes, so we're working in nanoliters. So opposed to benchtop, where you're injecting sample volume, with the micro GC, you're injecting with sample time. Generally, we work between 20 to 100 milliseconds for injection time, depending on sample concentration. The longer the injection time, the higher the response on the TCD. Something to also consider when injecting your sample is the sample conditions. You want to have minimal water in your sample, be non-condensing below 100 degrees, and be working below 1 bar pressure. We have lots of accessories to support sample introduction and sample management, which I will go into more detail later on. Then we have the columns. These take your traditional benchtop technologies, but are then shrunken down onto a much smaller scale, with a wide variety of options available, which I will go into in a moment. And then you have the TCD detector, where we're typically looking at working around 2 ppm limits of detection, all the way up to 100%. And this is really dependent on column chemistry and your target analytes. The TCD offers great linearity and fast auto ranging for high and low concentration samples. And some of you may have worked with the previous micro GC models in the past. On the 990 newer model, these components are now all independently changeable, whereas in the past you had to change an entire channel. So what this does, this makes the system overall much more serviceable, minimizes your downtime in the lab, and offers a much more economic system compared to those previous models. So as I mentioned, the micro GC can house between 1 to 4 channels, and these are really at the heart of the system itself. And you would have 1 or 4 channels depending on what your application needs are. So each chassis houses 2 channels. So you can see a single chassis on the left, which can house your 1 or 2 channels. And then for 3 or 4 channel systems, you would have 2 chassis connected by a heated bridge to ensure sample integrity. Really nice feature of the micro GC is that you can start with a 1 or 2 channel system and then easily upgrade to a 3 or 4 down the line as your target analyte list develops over time. And when it comes to choosing specific channels, it really comes down to what you're looking to analyze and what column chemistry is suitable for your application. We have a wide variety of column phases available in various lengths from 4, 10, and 20 meters long, depending on your application needs, as well as having the pre-column for those back flush capabilities. Like I mentioned, choice all depends on what you're looking to analyze and what your expected concentrations are. We are always more than happy to help configure a system to suit your application needs and work with you to make something that is suitable. So just to go through a list of some of the common channels that are available. We have the MolSiv channel, which is used for analysis of kind of target compounds, including permanent gases, methane, carbon monoxide, nitric oxide, and hydrogen, and is used in the natural gas and biogas analyzers. And then you can see a range of options available for hydrocarbon analysis. We typically say you work between C1 to C10 very comfortably on the micro GC. And then one not mentioned here on this list, but that we do have also available is the volamines channel, which can be used for ammonia analysis type application areas. So I'll just talk you through the principle of operation of the channel. Each channel is independent of each other, and we'll see kind of the workflow through a single channel here. So what we have is the carrier gas entering the system on the left-hand side through the proportional valve, and it's controlled down to pressure for whatever particular method you're looking to run. And this carrier gas will pass through the flow path on both the analytical column and the reference column flow path and to the TCD detector. Then you have your sample injected in the sample path and through the injection control. This will then fill the sample loop where it's mixed with your carrier gas. This will then travel into the analytical column flow path to the TCD detector, where we'll get an analytical measurement of carrier gas plus our unknown or sample. While on the other side, we'll have a reference of just carrier gas. So we'll have, what we're effectively doing is measuring the difference between our reference or known versus carrier gas containing the sample information. And this is measuring the difference in thermal conductivity. So it's really important to consider our carrier gas here. We need to identify what components we are analyzing and then choose a suitable carrier gas to give us that optimum difference in thermal conductivity to reach those low ends of sensitivity. So, for example, if we were looking to analyze nitrogen from this list, we wouldn't choose argon as a carrier gas because they have very similar thermal conductivities and you would get a poor response from the detector. What we would do is we would choose helium as our carrier gas in this example, as it has the highest thermal conductivity and will give us good response of target analyte versus carrier in our TCD detector. So the Micro GC has a number of accessories to ensure that you can effectively and simply introduce your sample into the system. We have on the first three, we have from the left-hand side, we have sample introduction accessories, and then we also have sample management accessories on the right-hand side as well. So the Genie filter and sample pressure reducer, and all these tools ensure reliable and repeatable runs. So I'll just walk through each of these accessories in a bit more detail. So the microgasifier controls liquid petroleum gas and liquefied natural gas sample evaporation before introduction into the GC injector. This also allows high pressure samples to be reduced without creating cold spots and preventing sample discrimination. The manual injector, syringe injection allows you to inject gas samples via an optional inlet on the front of the Micro GC, but you can also introduce the sample through a septum cap or by using a Lua lock connection. And this is ideal for small sample amounts or labs with samples from different locations, with various different samples from different locations. Then the stream selector, this is a really nice tool. I think it uses a dead end and flow through automated stream selection, which really simplifies and automates sample switching and freeing up time in the lab for a user. It's a really nice tool for cross-referencing data from multiple sample streams on a single Micro GC. And this can also be used for connection to calibration and or gas standards as well. So really simplifying those workflows for you. And both the dead end and flow through valves can be offered in 6, 10, 12 or 16 ports. So lots of flexibility and options there available for that sample introduction. So then on to the kind of sample management side of thing. We have the Genie filter. The Genie membrane filter uses a semi-impermeable membrane to remove droplets and particles from your sample gas stream. And this ensures proper injection for long-term reliable results. And then finally, we have the sample pressure reducer. This is a Beswick pressure reducer, and they're factory tuned to 0.7 bar and have a needle valve flow set to 20 mil a minute. And what this means is you have trouble-free compatibility with your gas sample for injection into your Micro GC. These are side-mounted and can be fitted with or without a Genie filter as you see fit. And the working range for the pressure reducer is between 0.5 bar to 200 bar. And as you can see, all these accessories are side mounted on the 990 Micro GC. Another nice accessory, kind of focusing on the portability of the system. This is a variant of the Micro GC, is the mobile Micro GC with carry case. This is a Pelican field case, and if any of you have worked with this type of field case before, know that this is an industry standard case. It's very rugged, watertight, crush-proof, dust-proof, and has a number of features like trolley wheels and handles to help with that portability and ease of use. Another nice feature is the lid has a start-stop function, meaning that the instrument will not analyze unless the lid is open. And what this does is save you both battery power and carrier gas when you're out in the field. And on that subject, kind of a bit more detail on the carry case itself of the system. You have built-in batteries in the system, has 2 rechargeable 8-hour batteries, so giving you a total of 16-hour power usage out in the field. And then also has these 2 gas canisters with quick release for fast replacement, which are refillable for your carrier gases when out in the field. So really nice tool for portability. And then on the subject of portability, we also have a Wi-Fi dongle that you can connect to this system, and what this allows you to do is remotely control the system, say on a iPad, which really gives you that truly portable system without needing to be by the system when operating it. So really nice tool there. So as well as the mobile variant of the Micro GC, we also have the 990 Pro Micro GC, which is a dedicated online and at-line process tool. This variant gives you fast, accurate answers to control your processes. In addition to all the standard features of the 990, the 990 Pro is designed specifically for online process environments with onboard data collection, integration, and results generation. This system serves many different industrial gas analysis applications, ranging from natural gas calorific value, composition, odorants, to name a few for that sector. And then you have things like refinery gas composition and trace level contaminants down to low ppm levels in industrial gases. There are optional extras as well with this system to be 19-inch rack mounted and also come with an ATEX enclosure. Also, a nice feature of this is no local operator is needed, as the 990 Pro monitors your processes 24/7 and communicates the analysis results directly to your process control, ensuring optimal conditions or follow-up actions as required. So just on that in a bit more, the onboard intelligence ensures complete operation from the GC control, data collection, data integration, and results transferred through industrial communication protocols such as 420MA, Modbus, or FTP service, just to name a few. This complete system allows you to control processes by directing automatic user-defined information to an external system, eliminates the need for an external computer by using our onboard setup feature, and meet industry standards with confidence through various different communication protocols. So now kind of covered the system in overview. We've kind of nicely coming into control software here. So I'll just cover a few different options that are available there. Agilent have the Open Lab software, which is their general operating software for all their platforms in their portfolio, which is compatible with the Micro GC. But we do also offer a couple more options as well, which are dedicated Micro GC softwares as well. So the first one is the Agilent Pro Express, which would control the mobile and process systems that I've just gone through. And then we have for lab and process systems, we use Soprane software, or Soprane 2 software, sorry. And we work with our partners, SRA Instruments, who are based out of France and Italy, who have developed software specifically for ease of use of the Micro GC in mind. So I'll just talk us through Soprane software in a bit more detail. Walk through the process, starting with configuration. It's very easy to set up an analyzer. It communicates via IP address with the software, and it'll automatically identify the channels and configurations you have on your system. This is where you would choose your carrier gas for each system, as well as the sample introduction, be that through single sample inlet or gas stream selector. What we then have is the status page. This will give you a nice overview of the heating at different stages through the system. So here you can visualize heating of the inlet heating, injector heating, and column heating, as well as information on the carrier gas pressure and detector as well. This slide shows a 2-channel system, but this would be adjusted to the number of channels on your system, all nicely visualized on a single page. And then moving on to our method editor and setting up a method. here we'll just talk through how this is a very simple process. This is either done and set through application note, or if you have a specific analyzer, be that natural gas analyzer or refinery gas analyzer, or we can help support optimize your method conditions as well. We are happy to work through that with you too. And I'll just talk through the common parameters here that you see. So at the top, you have the 3 parameters I'll go through first. First, you have sampling time at 20 seconds. Typically, we would sample between 20 and 40 seconds. And this is how long the pump is on and actively drawing your sample. This then flushes the analyzer, fills the sample loop with that known fresh representative sample. We then have sample inlet temperature set to 90 degrees here. This is very application specific, so it'll be set to your specific requirements. And then we have run time. This could be anywhere between 30 to 180 seconds, say, very much, again, dependent on application. This is a natural gas analyzer example, but if you were looking to analyze something like hydrogen, this can be done in as little as 35 seconds. So that's the top. Then here you have columns and their specific parameters for each of these, and these are all set independently, dependent on column chemistry and what you're looking to analyze. So here you have injector temperature, column temperature. Again, this is held isothermally, opposed to traditional benchtop, which is ramped. Holding isothermally gives you those quick startup times, and you have no need for cool down between each run. So you've got really fast, minimal time between each run. Then you have injection time, and this is how much sample is being injected from the sample loop. And then we have things like column pressure, backflush time, if it's applicable, and making sure your detector is turned on. So just to talk through backflush, this requires a little bit of optimization, and our engineers work with you on installation to achieve this, to set up your method. But here I'm just going to talk about backflush tuning for methane and preventing heavier eluting compounds from entering the channel. So what you see here on the y-axis is channel area, peak area for methane, and then you have backflush time on the x-axis. So you see before 25 seconds, we aren't seeing a methane peak, and then after 25 seconds, we start to see a methane peak develop. And at 27 seconds, it has the area of that peak has reached its maximum, and so we're not going to be seeing any more methane as we keep pumping sample into the flow path. So at this point, anything that comes in is going to be a heavier eluting compound. So this is the perfect point to apply backflush. That then sends the rest of our sample in our sample loop out to vent, and all we're seeing in the system is our peak for methane. This is great for improving run times, shortening those run times, as well as removing any interference from the next run in our sample portion. The next stage then is calibration. Once you have your method and your backflush all set up, typically you calibrate for your target analytes. If you're analyzing multiple target analytes, you will need to know, have a known amount for each of these to identify and integrate the peaks at their retention times. And you can choose to do one level if you're doing a wide range of concentrations, but you can also choose to do a number of points for calibration as well. Once this is all carried out, this can then be saved into the software. So that then leads me on to results. Here you can nicely visualize the output of the analyzer. Each channel generates its own chromatograph, as well as one that is completely normalized for the entire run as well, once complete. And a really nice thing, I think, about Soprane software is the ability to do trend analysis, which is kind of a really important feature for using the micro GC as a gas analyzer. Previously, you would have to manually export your data to Excel and do the plotting yourself. But with Soprane, you can automatically plot trends by selecting data over a period of time, be that a day, a month, a year, and it will plot your compound selected. And this is a really nice feature if you're looking at monitoring, say, a reaction or want feedback from your process. You can identify those spikes and drops in compounds really simply. So it gives you just a nice overview of your sample over a period of time. So that is an overview of the system itself and its capabilities. So now I just wanted to discuss some specific application areas. Here you can see kind of an overview of the different application areas that the micro GC is used in: natural gas, energy, environmental, and reaction monitoring. Natural gas is probably the biggest market for the micro GC. Mud logging analysis is probably the best representation for demonstrating the speed benefits of the micro GC. Then into the energy sector, things like biogas analysis and fuel cell monitoring are really nice applications for the system in clean energy sector. And then, like I mentioned, reaction monitoring as well is really popular in the UK for the system, and we see a lot of research institutes and universities using it for that type of analysis. So I'm just going to go through a few of these application areas in more detail and apply the system to those application areas. So first I'm going to talk about mud logging. This is a process of obtaining information about lithology and fluid content of a drill area. The monitoring of gas, both in type and amount, is one of the most important tasks in mud logging. Accurate gas data recorded during the drilling are really of great value in proper reservoir evaluation and may pinpoint potentially overlooked producing zones. Gas chromatography as a technique is primarily used for the gas identification, the identification of the gases and measurement during this process. The most common components in mud logging are methane, along with heavier compounds such as ethane, propane, and butane. And sometimes heavier compounds up to C7 may also be required to monitoring. These heavier compounds can indicate an oil or wet gas zone in the drill site. Analysis speed is really important in mud logging because the more detailed information you generate from the unit drilling depth, the more accurate the reservoir evaluation can be. So the Agilent Micro GC is an ideal system for the fast and reliable analysis of well gas. So we'll just talk through the use of the system in a bit more detail. This study I'm going to go through demonstrates the analysis of hydrocarbons in mud logging process using the 990 Micro GC, and it was equipped with a two-channel system, two analytical channels for the analysis of C1 to C5. On the left-hand side of the slide, you can see a description of the analyzer, sample type, compounds of interest, and their typical quantification range. The channels used were a 10-meter Poroplot Q channel with backflush capability. This was used for the analysis of C1 and C2. The backflush option was deployed to flush the heavier components out from the pre-column before they enter the analytical column. And this helps reduce analysis time. Otherwise, the analysis would last much longer due to those heavier compounds eluting later onto the channel. As well as this, the Poroplot Q column was used for CO2 peak determination as well. You can see that in this chromatograph here from the natural gas standard as well. And then on the right-hand side, you can see that the 4-meter Poroplot Q without backflush was used for the analysis of propane, butane, isobutane, pentane, and isopentane. And the results table below shows nice peak area precision for 10 consecutive injections on the two channels. with the RSD demonstrating excellent performance of the micro GC, guaranteeing qualitative and quantitative results with really high levels of confidence. So this study was used to demonstrate the fast analysis for mud logging using this two-channel system for the analysis of C1 to C5. But there is always the option to extend that capability by adding a third channel, and you can then configure to analyze C1 to C8 hydrocarbons. The analysis speed of each channel was optimized to be finished within 35 seconds. And the retention time and area repeatability were excellent, demonstrating that the 990 Agilent Micro GC is an ideal platform for fast and reliable mud logging gas analysis. So the next application area that I'd like to talk about is impurities in hydrogen. As we're all aware, there's a really big push for clean fuels in the energy sector, and hydrogen fuel is a versatile energy carrier that when consumed in a fuel cell produces only water and has zero harmful exhaust emissions. As a clean energy source, the application of hydrogen in fuel cell cars is really promising. There are various methods to produce hydrogen, and that could be electrolysis of water, coal gasification, or natural gas stream reforming, just to name a few. And these different methods of producing hydrogen may introduce impurities into the hydrogen product. When hydrogen is used as a fuel cell, those impurities may damage the cell. So impurities like helium, neon, nitrogen, argon, or methane will dilute your hydrogen concentration, making it a less efficient fuel product. And then compounds like carbon monoxide and carbon dioxide can damage fuel cells, so will decrease the lifetime of those fuel cells. So with this in mind, it's really important to detect ppm level impurities before hydrogen is used in fuel cells. The micro GC can provide fast and sensitive analysis for 2 to 10 ppm level hydrogen impurities analysis. So we'll just go into the data in a bit more on this application. Same layout as the previous application. You can see the configuration, sample type, compounds analyzed, and typical quantification range on the left-hand side. And I'll just talk through the chromatograms in a bit more detail. So in this application, high purity hydrogen with 99.9995% purity carrier gas was used for this test. Hydrogen has probably the highest thermal conductivity, so it's a really good fit as a carrier gas, and provides excellent sensitivity for these components we're looking to analyze. As well as its sensitivity, hydrogen as a carrier gas eliminates matrix effects in this application too, so you get a double benefit from using it as a carrier gas. Two gas standards were used with a mix of target analytes, with most of the components being concentration range around 5 to 10 ppm in this application. And you can see that 2 straight columns were used, so no backflush in this application. We have a 20 meter mole sieve and a 10 meter poroplot U channel. And these were used to detect and separate compounds from helium to carbon dioxide. So on the chromatograph on the left, this shows the helium and neon are well resolved on the 20 meter mole sieve channel. And then the right shows the detection of argon to carbon monoxide, and these are in the 5 ppm level concentrations, and you see nice baseline and peak separation is all well identifiable as well. And the separation of argon and oxygen is also well finished with a resolution value of 1.13. And just on this mole sieve chromatograph, I just want to draw your attention to the methane peak here compared to here on the poroplot U. This response is much higher on the poroplot U than in the mole sieve column. So the quantitative analysis is suggested in the poroplot U here together with the carbon dioxide. So again, a repeatability test was run on 10 injections, and you can see the results in the table on the right-hand side. This shows all components had excellent retention time RSDs, and the value is below 0.1% of the peak area RSDs, and the area values are all smaller than 5%, except for that of oxygen, which is 5.28. So this application brief really demonstrates the applicability of the 990 micro GC for fast analysis of impurities of hydrogen. The results show excellent retention time and peak area repeatability, with a total run time being less than 150 seconds. So this is extremely helpful if you're looking to make quick decisions on your hydrogen quality during manufacturing processes. Then the last application area I wanted to talk about was natural gas analysis. As I'm sure many of you are aware, natural gas is a source of energy used for heating, cooking, and generating electricity. It can also be used as a fuel for vehicles, as well as chemical feedstock for manufacturing things like plastics and other important chemicals. Natural gas is a naturally occurring hydrocarbon mix, primarily consisting of methane, but commonly includes varying other amounts of hydrocarbons such as ethane, propane, butane, isobutane, pentane, and isopentane, and sometimes a small percentage of things like carbon dioxide, nitrogen, hydrogen sulfide, or helium can all exist in this natural gas mixture. In most parts of the world, natural gas is traded on its energy content. Accurate information on natural gas composition can help generate the correct unit calorific value, which is really important when it comes to natural gas trading. The traditional approach to natural gas analysis is primarily based off regular benchtop GCs with really complex multi-column, multi-valve configuration with run times that typically take 6 to 20 minutes to complete, depending on what your configuration is and what your compounds of interest are. Compared to traditional GC platform, the Agilent 990 is obviously much smaller, consumes much less carrier and power, but more importantly, it can provide much faster natural gas analysis. The Agilent 990 micro GC analysis approach for complex gas samples is to analyze parts of the sample on different channels and then combine and normalize these results from the different channels to give you that complete information on your whole sample. And since each channel is only focusing on a subset of the sample, the method is really easily optimized for faster speeds without compromising on the important resolution. So just to go into this application in a bit more detail, there are 4 types of natural gas analyzers which are based off the 990 micro GC. Here on this table, you can see the natural gas analyzers. So we have A extended, B extended, and then these are defined by each of the channels that are inside the system. Each analytical channel in the analyzer addresses a different part of the natural gas constituents for your specific analysis requirements. And these analyzers are actually out-the-box solutions. So the analytical method on the analyzer is optimized in the factory and then verified by a simulated natural gas standard. And then to show validity of the method, these are then standards are taken to your site and replicated for you on installation. So here you can see the options available in the table. Today I'm going to talk through the natural gas analyzer B extended because it's got all the bells and whistles on it. It's got can do full range, do hydrogen sulfide separation, low ppm hydrogen analysis, and nitrogen oxygen separation, as well as helium and neon separation, depending on carrier gas that is used on the system. Again, configuration can be seen here. We've got MolSiv, again, PoraPlot U, and CPSIL. The first 2 columns have backflush capabilities. Sample type is natural gas. talk through our compounds of interest, and we have their typical quantification range. And you can see here that this system is also follows various industry standard methods as well. So I'll just talk through the different chromatograms generated by the system. At the top, we have the mole sieve channel with backflush capabilities. This enables the analysis of those permanent gases in the natural gas. So this includes helium, neon, hydrogen, oxygen, nitrogen, and methane. This column type achieves baseline separation of those permanent gases at or above ambient temperature without expensive coolants too. So both argon and helium can be used as a carrier gas in this channel. Helium is used for nitrogen and oxygen separation, which you can see on the top left-hand side. And then if you're looking to do low concentration helium or full range hydrogen analysis, argon would be more well suited. And you can see that here on the right-hand side. Another important point I'd like to bring to you in this bottom left chromatograph is the measurement of hydrogen sulfide. This is really important for gas quality specification because of the corrosive nature of hydrogen sulfide. Can have an effect on your pipeline material or utilization equipment. So it's really important to identify if this is present in your gas mixture. So here we have the Poroplot U, which is really well suited for this type of analysis. You can see good peak shape here for your hydrogen sulfide, as well as methane and air all being well resolved on this channel. The heaviest compound analyzed on this channel is propane. If any heavier hydrocarbons were to be analyzed on this Poroplot U channel, they would elute much later using the conditions we have for hydrogen sulfide analysis, which would lead to tailing peaks at this applied temperature, which is why we also adopt the third channel, the CP-SIL. This doesn't have backflush, so it's just a straight channel for analysis of propane to nonane. And here you can see bottom right hand side that hexane eluted within 50 seconds, octane eluted in approximately 3 minutes, and nonane takes approximately 5 minutes to detect. So this is showing you a nice analysis of C3 to C9 components, where propane can be analyzed on both those channels mentioned, sort of as a bridging component for the two. Another nice feature that I just like to talk about, which we did touch upon earlier, is the software used for this, the ProExpress. The economic value of natural gas is determined by several key properties, including calorific value, compressibility, warp index, and so on. And by following international standards, these properties can be calculated from the concentration of each identified compound in natural gas and its specific physiochemical properties. The natural gas analyzer allows you the collection of data to identify and quantify these natural gas constituents. These results are then fed into this reporting software, which then calculates those critical physical properties following a number of standards such as ASTM, GPA, and ISO methods. And the calculated results are then available for reporting, monitoring, trend plotting, and exporting. So really nice feature from the software there. So just to summarize here, the natural gas analyzer B extended can address the analysis of permanent gases, hydrogen sulfide, and other general constituents of natural gases, so those hydrocarbons up to C9. And the backflush options are used to protect the analytical column from those heavier contaminants and keep each run free from those interference of the heavier compounds from the previous run. So just to summarize, the Micro GC offers really rapid analysis times, operates isothermally, so you're held at temperature, so quick startup times and minimal time between each run, and offers really nice reproducible data. Really compact system, both physically and environmentally, which makes it great for both lab and in-field system. It can be applied to a number of industry standard methods, and also has that future-proof flexibility through the options to upgrade the number of channels depending on what your requirements are and as they develop. And then compared to previous models, that serviceability by being able to fix those individual parts in each channel makes it minimizes downtime and gives you a much more economic system. So thank you for listening. Happy to take any questions.
Brilliant. Thank you very much for that, Hemi. That was a fantastic overview of the 990. I'm sure everyone agrees. We've probably only got time for a couple of questions. One has come in about the mobile setup. So it says, can you switch between the mobile setup and the lab-based instrument?
Yep. So they're two different variants of each other. If you have lab chassis and mobile chassis, you can take the channels from either of those and swap those independently, which allow you to have both a lab system and mobile system.
Okay, perfect. Another one says about carrier gases. Is it possible to have different carrier gases for each channel within the system?
Yes. So you can have different carriers for. You can use different carriers for the channels. They can be swapped around dependent on your application needs. These can be changed when you see fit, and all you need to do is just ensure that the your software has the correct settings as you change that carrier gas.
Perfect. Lovely. Okay. We've reached the 50-minute mark now, so we'll draw the webinar to a close. So okay. Thank you, Hemi, for the presentation. Thank you all for joining us today. Hope you've enjoyed it. The recording will be available, so if anybody does want that, they can contact us after the event. So thank you all very much for attending, and enjoy the rest of your day.
Thank you very much, all.